Okay, let's try to write formulas for these polynomial functions. We're given the graph, and the easiest way to go about this is to use the end behavior and the intercepts. For the x-intercepts, we can actually see the multiplicity. Let's start with the x-intercepts for this first one. So if we write this out, if x is -1 and x is 2, the output is 0, so those are x-intercepts. And you can see that right at -1, the multiplicity is 2 because a function looks like a parabola right there. But for x equals 2, the curve crosses the x-axis pretty much like a straight line. That's a degree 1 behavior, so the multiplicity will be 1. Now the end behavior, as x goes to infinity, the y behavior goes to -infinity, and as x goes to -infinity, the y behavior goes to +infinity. And what this tells us is that there's an odd degree for the polynomial and also a negative coefficient, negative leading coefficient. The last thing that I can see there is that the y-intercept, when x is 0, the y-intercept is 2. So we're going to put that all together and figure out a formula, the least complicated formula for this function. Well, I need an x minus -1. That's the 0 when x is 1, but multiplicity 2. And x equals 2, the factor is x minus 1. The multiplicity is 1, so I could put an exponent of 1. I normally don't need that. And I need a negative coefficient, so it has to be negative something. And let's just check if x is 2, I'll have something negative times 0 minus -1 is 1 squared times -2. And just with a coefficient of 1, I'll have -2 times negative, and I need to get a 2, so I'm already set with a coefficient of 1. So let's just put a box around this, and we found it. We've matched all of that information. The x-intercepts, the y-intercept, and the end behavior are telling us that it's a third-degree polynomial, negative leading term, and a double factor at -1 and a single factor at 2. Okay, so let's erase, and we'll go to the next problem. The next problem is exercise 52 at the end of the section. And we're seeing this. Let's just go through the same information. First, when x is 0, the y-intercept is at -3. That's right there. But I'm seeing 4 different x-intercepts. And you can see that if you zoom in, the curve just crosses at those 4 points like a straight line. So those will have multiplicity 1 for each of those. And those are at -3, at -2, at 3, and at 4. So this means that the degree will be at least 4, and I think we'll be able to build this up using that degree. So f of x is going to be some leading coefficient times these factors. The x-intercept, or the 0 of -3, gives a factor of x plus 3. That's actually x minus -3. The other one, x plus 2, x minus 3, and times x minus 4. Those are 4 factors, and we're still wondering about that leading coefficient, that coefficient. I can see that it's going to be negative because the end behavior, as x goes to infinity or -infinity, the end behavior is negative, so I must have a negative number. But let's see what happens. We're going to match this with the y-intercept. F of 0 is going to be some coefficient times 3 times 2 times -3 times -4. This all multiplies to give, what is that going to be? 24. Well, actually, it should equal it should equal -3. And so we could see here's a factor of -3, there's a factor of -3. So these other things cancel out. So this really has to be 1 over 2 times 3 times -4, so that those cancel out, and that's 1 over -24. So we can put this all together. Let's put in the coefficient, -1 over 24 times those 4 factors, and that's going to be a degree 4 polynomial that has those 4 x-intercepts, each of multiplicity 1, and with that -1 over 24 leading coefficient will match the y-intercept as well. Okay, one more of these. Let's erase this and go to one more of these. The last one, I can see some interesting multiplicity going on there. And this is number 56 at the end of the section. And I can see, just building up this table, the x-intercepts are -3, -2, and 1. And that's where the output is 0. And notice that at 1, this behavior, it has a multiplicity 3. Because right up close, it looks like a cubic. But the other 2 roots, those look just like straight lines, so those have multiplicity 1. How about the y-intercept? If x is 0, y is -1, that's right there. And then end behavior, as x goes to positive infinity, y is going to positive infinity. And as x goes to negative infinity, y goes to negative infinity. And so the end behavior tells us that it's going to be an odd degree polynomial, and the leading term is going to be positive, is going to have a positive leading coefficient. So that's interesting to know. And the multiplicities add up together to give 5. So that means that the degree is going to be at least 5. And if we just take those into account, we can get a function, a polynomial that has degree exactly 5 by doing the following. We're going to have some coefficient that we'll figure out later, and x plus 3 is a factor because of the -3 root. X plus 2 is a factor, and x minus 1 is a factor, but that x minus 1, since that 0 has multiplicity 3, we'll need to raise that to the 3rd power. And you can see that's altogether, that's degree 5. So that's going to be as small as we can do. But let's just check with the y-intercept and check what would f of 0 be. We're going to have a 3 times 2 times -1 cubed. That's a -6. But the answer should be -1. So this coefficient should be 1 over 6. And let's erase this coefficient and put in 1 over 6. That's going to be the polynomial of least degree, degree 5, that matches that critical information. So there we go. That's the 3rd example, and we'll move on to problem number 5.